we'll start with clay balls. 2 balls of clay are thrown at each other in such a way that once they hit, they stick together. The first ball has a mass of this and is moving at this direction. It's measured counterclockwise from the x-axis. So x-axis and then upwards, counterclockwise. Second ball has a mass of this and is moving at a speed of this in a direction blank degrees measured clockwise from the x-axis, so kind of towards the x-axis and then going downwards. Once the clay ball is joined together, they move in the x-positive direction. Okay. So let's look at the y for this. This is clay. What must, remember your y's for these have written and vectors, right? So your understanding of it conceptually, and then also do a vector diagram and the momentums involved. So what must be true during the system during this situation? Correct. What before must be equal to what after? The momentum. That's key. Momentum before must equal momentum after. Oh, I added an E. That's because in my mind I was starting to write the E, the equal, before I switch lines. So what happens when your mind is going faster than your hand and it's Friday afternoon. So let's see. How is the momentum and the velocity related to each other? Think back to the tasks we did yesterday. What was true about the momentum and the velocity? Okay, so we have our equation, right? We have our equation that momentum is mass times velocity. I was thinking more along the lines like the direction. Excellent. That's what I was getting at. Perfect. Nice. Thank you. So the direction, and you put it very nicely, direction of velocity is the direction of the momentum. All right. So that's probably that's a good showing understanding here. Maybe one other thing, but I think we'll handle that in the in our vector diagram. All of these are about momentum being conserved. So in your y, if you haven't addressed the fact that the momentum is the same before and after whatever happens, go back and add that to your y. That's needed in every y in this concept. So now we need to do the vector part of this. So I've got the first clay ball coming in. I'll call it clay. I'll call it number 1, and it's at a direction 33.6 degrees as measured clockwise from the x positive axis. So my x positive axis goes in this direction, and 33.6 degrees would be something like that direction. So that's momentum 1, because it's in the same direction as velocity 1. I'm having a hard time concentrating, so if you guys can do it a little bit lower, I'll come back there. Okay. And then I'm looking at ball 2 now, and it's at 47.6 degrees clockwise from the x-axis. So clockwise would mean down, so it's going to kind of be like that. That'll be the second momentum. Does anyone see how I got those directions? Or anyone have a question about how I got those directions? All right. And then it tells me that once they hit, they combine, and they move together, their new velocity is just in the x positive direction. That means afterwards, so this is after, and this is before. Probably should have started off by labeling this. But afterwards, they combine into a single thing, right? The clay balls combine into one object, or they move off together. So it's kind of like, boom. And I know from what I wrote that if I add up the green and the red, it's gonna equal the blue. So that's the premise, that's the concept that I'm gonna use on the how side here, mathematically find whatever they ask me to find. So let's see what they ask me to find. What's the speed of the first ball of clay before the collision? Because they told me what direction it is, but not how fast it was moving. And what is the speed of the combined balls of clay after the collision? So, got to find some things about speed here. First thing I'm going to do is I'd rather make the math easier on myself, so I'm going to break everything into X and Y, do the components. So for the red one, it's going up that direction. We said it's momentum 1, which means it's mass 1 times speed 1. And then I draw its components, and I know this angle. That angle is, let's see what, 33.6 degrees. And then I can draw this one. And it's going to have components. Oh, I don't want to draw those components. Excuse me. I drew the wrong components. We have this one. This green one is just not agreeing with me. And so the hypotenuse is the momentum of number 2, which is mass 2 and speed 2. And this angle, was that 40 something? 47.6 degrees? And this component faces this way, and this one this. So now, since I have right triangles, I can use my knowledge of right triangles. So I know this side is M2 B2 cosine 47.6 degrees, and this side is M2 B2 sine 47.6 degrees. And up here I have M1 B1 cosine 33.6 degrees and M1 B1 sine 33.6 degrees. Lots of numbers, but it's going to make our life easier because now we can look at just the X direction or just the Y direction. And then, do I need to find the components of the final momentum? No, why? Because it's in the X direction. It's in the X direction. Well, sorry, what? Right. I'm just looking, right now I'm looking at, I had to break P1 into 2 parts because it points in both the X and Y direction. And same with P2. But the total only points in the X direction. So it only has an x component, and it's m total times v total. That's my point. Is it's not going to have an x. Well, how much of it is in the y direction? What do you guys think? How much of the total momentum here is in the y direction? 0. So I've kind of done that in my head already, right? So, okay, so now as Mikhail said, if we look at these just as horizontal and vertical parts now, so we kind of forget, you know, that this part of the triangle exists and this part exists. So we just have the horizontal and the vertical parts. All the horizontal, if I have all 3 horizontals, the red plus the green has to equal the blue. And if I add up the verticals, the red plus the green, what do they have to add up to, the vertical part? 0. So they want me to find V total and V1. I think I'm going to start in the y direction because there's one less thing to worry about, right? So I'm going to add the red to the green in the y direction. The y here. Which way should we call one direction positive and the other negative? Okay, which one do you want to call positive? Up and then also, and we'll call it to the right. So up is positive and also to the right is positive. That works. So I want to say that the momentum before, the red plus the green, that's the momentum before the collision, equals the momentum after the collision. So the momentum before the collision would be positive m1 v1 sine 33.6. I'll move up on the board in a minute. And then plus negative, so that's minus m2 v2 sine 47.6 degrees. And that's going to equal 0. I probably should have done those in my other colors. So this is the red vector. This is the green one. And they add up to be the blue part there. Everyone see where I mean, it looks nasty right now. But let's put some numbers in and see what we know and what we don't know. Okay? Do we know the mass of the first blob of clay? Let's see. The first ball has a mass. Oh, it's right there, right? Mine's 1.87. What's yours? There you go. 1.8. Good. I think for room, I'm going to leave off the units. Is that okay with everyone? Okay. Do I know the speed of the first blob of clay? No? Don't be disheartened. It's always good to have one variable. Sine of 33.6 is just a number. Granted, it looks nasty, but it is just a number. And then, let's see, the mass of the second blob of clay, for me, is 5.2. I'm assuming yours is close, right? You have 5.2 also? Cool. You got 1.6? And then how fast is that one moving? Mine's moving at 4.9. 4.4, so close. So 4.90 sine 47.6 equals 0. So I could, I've got all numbers except for that one variable. So let's pull out the calculator and make this look a little less nasty. So 1.87 times sine of 33.6 for me is V1 minus times sine are your angles measured in degrees? Then you want your calculator in degrees. That looks a little more manageable, right? I'm not done yet, because I still have V in there. If you get a negative and you haven't made a math mistake, all it means is that somehow you picked the wrong direction for your velocity, but you shouldn't get it. You shouldn't get a negative. Are you sure that your calculator is in degrees? Check that. Bring your calculator up and I can show you, because my one for the screen still isn't working. I get an answer of 18.2. Let's go on to B. So we did this by looking at the y direction. What do you think we have to look at for the for B? The x direction. The x direction. So I still have. This is going to be fun because I've got to go back and forth. So this is in the x direction now, and I'm going to have the momentum before, which. So I'm going to have this, the M1V cosine 33.6 plus the other horizontal part, M2V2 cosine 47.6. They're going to add up to the total, the blue arrow, right? So red horizontal plus green horizontal is blue horizontal. So I'm going to try to remember all that as I write it down here. Red, so M1V1 cosine 33.6 degrees plus, because this time they're heading in the same direction. So remember, this is one of the crucial things about trying to draw these vector diagrams as accurately as possible. They tell us whether our terms are positive or negative. So because both these point towards the right, they're both positive. And so is the one afterwards, right? Yeah. So that's why it's good to be kind of careful about drawing these. 47.6. And that has to equal mass total, velocity total. Oh, I know V1 now. Yay! One more piece of information. It's like it was planned. So, let's see. My M1 is, I've got no clue at this point. 1.87 again. V1. Now, if you can use the whole number, use the whole number so you don't have error. Cosine 33.6. And plus, and my M2 for me is 5.2. Moving at 4.9. Cosine 47.6. Oh, look at that. That whole left side is nothing but numbers, right? Yay. My total mass. How much, when these two blobs of clay join together, how much what's the mass of them going to be? How would I find out once these two hit and join together? How massive are they going to be? Add them, right? So for me, that's 1.87 plus 5.2, and then B total, I don't know. For a second, I thought I wasn't going to have a variable. It's no fun to do an equation and not have a variable. It takes away your whole afternoon. So I'm going to figure out what these numbers are. Cosine 33.6, 28.32019 plus well, okay, or I can answer it as I'm doing this. What's up? No, I can. I will. But I was thinking maybe I could answer it without. Oh, I got that from my part A. See my 18.2? Unrounded, that's 18.1823299, all those fun numbers in my calculator. Okay, so it looks like I have to add the 28 and the 17, right? And I get, so this side is now 45.5013. And then divide both sides by 7.07. And I'm going to come to my total. I get 6.45. Nope, 44, sorry. Meters per second. All right, so folks, firecracker is the next one that we're going to talk about. We have about 10, 12 minutes left, so I'm going to talk a little bit faster just so that we can kind of cover it. But don't forget to do the exit ticket. It's up in Socrative. It's already live. Make sure that you check in and do that before the block ends today. So firecracker. This problem, really, we can look at it as two separate parts. We've got the part where the firecracker is dropped and it accelerates as it falls down, and then we have the explosion. So it's the fifth one of the series if you're looking for it. But so we need to treat those separately because it's a projectile when it's falling, and then it gets down to the bottom, then it explodes, and it's the explosion that we're going to look at with momentum. So in your Y, I would have things like when dropped, excels downward. How fast? What's its acceleration downwards? 9.81 meters per second squared. Excellent. I might even put in here that it starts from rest. That's our definition of dropping. You know, you're not throwing it up, you're not throwing it down, you're just letting it go. So it's starting from rest. And then I'm going to leave a space. The next concept is the fact that then it explodes. When it explodes, momentum is conserved. Diagram-wise, remember I'm going fast. I don't expect, you might want to just watch rather than trying to do it also. Before, you just have momentum down because it's just dropping straight down, so its velocity is straight down, its momentum is straight down. Afterwards, one piece has momentum in this direction, call that P1, and the other piece has momentum in this direction, P2. How do their masses compare? The mass of P1 compared to the mass of P2? They're the same. What's the beeping? Huh? Oh, you okay? You good?
Yeah. You get really annoying on days when that's changed.
You're good. No. Okay. They have equal inertias, equal mass. So how do you think they split up the momentum? Equally, right? So as much momentum as piece 1 has, piece 2 has the same amount because they split the mass equally.
So the P1 and P2 would be the same number?
Yes. Yes. Now, that doesn't mean like if P, the red one, was 10, would they be 5 and 5? No, yeah, right, because the direction matters. So they're going to actually be bigger, like they would be 7 and 7 or something, because they're pointing in at a direction.
Okay.
So think about like the sides of a triangle. They don't add up to the hypotenuse unless you take into account the direction. So that's what we're going to do over here. I'm going to do a little sketch here. Let's see. P2 goes that way. I'm going to draw them the same color. I know they're the same size. They go that way. Let's see. It tells me mine is 110 degrees. I should have. So this in here is 110 degrees. If I drew a line across here, and I called both of those angles A, does everyone agree that there's some symmetry going on here? So A plus 110 plus A equals 180 degrees. Does that make sense geometrically? So what does A equal? $35 for me. 70 plus. So I'm going to draw, let's see. I got P1. It's going to have a horizontal and vertical part. This will be 35 degrees. I'm going to call that P1 again because they're the same size. Maybe I should call it, I'm going to call it P2. All right. The one other, how do I know how fast it was moving right before it exploded? You got to think back to the beginning of the year. V final squared equals V initial squared plus 2A delta D. All the way back to that beginning of the year. And I look and say, okay, if it was dropped, that's 0. I said it was accelerating at 9.81. And mine dropped a distance of 2.99 meters. And if I find V final here, that's how fast my firecracker was moving just before it exploded. Don't forget to square root it. Oops. So my firecracker was moving at about 7.66 meters per second just before it exploded. So now, over here, remember, so this, I don't know. Michelle, we got to find the manual on your calculator. So now I know how fast the firecracker was moving just before it exploded. I'm going to stop. I'm going to have to stop here because we only have a couple minutes.